some at noon 30. We have to finish at noon 20ish.
Okay, I'm telling.
Just send her an email.
Yeah, I'm sure he will be okay.
Hello, everyone. Welcome back. And please take your seats. And we are having 4 papers in this section. And we have to respect the schedule because we have a very important keynote at noon 30. And it's the time that he has. So we cannot delay, we cannot be late. So let's start with data flow optimization in smart accelerators, loop reordering, and loop tiling with Mingyu Gao. Please.
Okay, thanks for the introduction. So I'm Mingyu Gao. I'm currently an associate professor at Tsinghua University in Beijing, China. So I mostly do research on computer architecture, including the domain-specific accelerators, near data processing, and also some part on the hardware security. So today, although this talk is scheduled in the software optimization session, but it's actually about hardware or maybe the software scheduling on the hardware accelerators. So mostly we'll focus on the sparse accelerators, which is domain-specific accelerator for sparse computations, like sparse matrix, sparse tensor. Those sparse algebra applications appears in many domains, like machine learning, if you have a pruned sparse neural network, and also in big data or graph processing, if you have like some kind of sparse graph data that you want to do some analytics, and also some like graph neural networks, graph mining, etc. Those kind of like widely used in those sparse data structures. So we know that sparse accelerator is very irregular in terms of the data reuse because the data, the non-zeros is sparsely distributed in the tensor or in the matrix, so that the locality for the data access is very poor. Which means that it will become memory bound when you access data from the off-chip memory because the on-chip cache will be not efficiently used. And also the load balance is very bad. If you have many cores, if you have a many core architecture, like many CPU cores or the GPU parallelism, typically the different cores may have imbalanced workload assigned to them. So it probably will underutilize some of the cores while many of the computations are concentrated on some of the cores while the others are idle. That brings to the domain-specific accelerators that for sparse algebra, such as at least a bunch of previous papers that design specialized chip for this sparse algebra workloads. On the other hand, we know that since we know that the sparse computation is very memory bound, another well-known technique to improve the data access efficiency for the off-chip memory is the loop transformation techniques. Those are widely used in dense computations like matrix-matrix multiplication. For example, we have this A matrix times B to get C matrix. In this case, we have a 3 levels of nested loop, and we know that we can try to reorder the loop orders here, so that maybe IJK or IKJ or many others that could each order could optimize the data reuse of certain matrix like A, B, or C over the others. And also we know that we have loop tiling techniques. So we can, if the matrix is very large, we can tile it, we can split it into smaller tiles so that each of the small tile can fit in the on-chip buffer, on-chip cache, and to reuse data better. So the key question we want to address in this talk is how to apply the loop transformation, specifically reordering and tiling, to the sparse computation, sparse accelerators that we have mentioned. So there's some key challenges is the sparse accelerators have drastically diverse and varying sparse degrees and patterns. For example, if we look at some of the representative applications, for neural networks, we know that we can prune the neural network and make it sparse. They usually have very small matrices, and also the sparsity is not so high. So that means they have many non-zeros. It's typically on the order of, for example, the green dot is for neural network. The density is probably like 10% or even 1%, but the matrix size is only like for like 1,000 times 1,000, something around that. On the other hand, for the graph applications, so they typically have very large graphs, like up to the 10 to the 12 dimensions, And also their sparsity is very high, or density is very low. Like they can have like as low as 10 to the minus 5 or 10 to the minus 8 sparsity. So on the other hand, the sparse patterns, even if you have the same density, but the distribution of the non-zero data are also very widely. So some of them have like more uniform distribution. Some of them have like concentrated on some part, like a local region of the matrix, or like there's only like a diagonal type, etc. So these diverse sparsity patterns are very difficult for the sparse accelerators to handle. So for example, if we look at the loop reordering case, we know that for a sparse matrix, we can have 3 different types of orders here. So for example, here's MNK or KMN or MKN. They corresponding to different ways to compute this matrix multiplication. For example, this is the inner product. That means 1 row times 1 column to get 1 element of the output. And this one is 1 column times 1 row to get a partial sum of the whole output matrix, and you get many of that and then accumulate. And finally, you can also do like a row-wise data flow, that 1 element times 1 row to get 1 output row here. Okay, the essential thing is that they have different orders and corresponding to different ways of the computation. And if you look at the data reuse, you can see that different orders, these 3 ways, inner product, outer product, and the row base, they have different data reuse characteristics. Like inner product, they have very bad reuse for matrix B, but have like very good reuse for matrix C. Okay, or on the other hand, like out product, they have reuse B very well, but the C reuse is very, very poor. Okay, so that means if you have different matrix, different kind of data, you maybe want to prefer like different data flows for different data. Okay, different matrix will prefer different choices. Okay, so the key design that we propose, this is the XPLOS 2023 paper, which called SPADA. We want to propose is to make the execution flow, the data that how we compute this the data to be adaptive to the sparse patterns. Okay, so basically based on the data characteristics, we choose one of the 3 or one of the data flows that are best that are the most efficient to compute this specific matrix. So to achieve this goal, we first need to propose adaptive data flow abstraction, okay, which is we call it window-based adaptive data flow. And then we need to have a reconfigurable, like a flexible hardware to support this reconfigurable or this adaptive data flow, to support these different ways. And then finally, we want to have a runtime policy to see, given a matrix, which policy we should use in those cases. Okay. So here, this is the adaptive data flow that we propose. We basically say we have a window of the A matrix, and then times the corresponding, for example, this one is times to the 2nd row, this one times to the 3rd row, and this one times to the, we'll multiply the first row, etc. We multiply the element in this window to the corresponding rows of the B matrix. Okay, this is actually an extension for the row-based data flow that we have mentioned before, the last choice in the previous slides. Okay, so the trade-off here is that we can adjust the size of this window. Okay, so I think the animations have some issues, but the basic idea is that if you make the window very short but very fat, so basically make it flat, it will approach the row-based data flow approach. Okay, so it have better reuse for the input for the output matrix. On the other hand, if you make it very tall but very thin, the window it will approach the outer product approach that will reuse the input matrix better, but you use the output matrix worse. Okay, so sorry for some of the format issues here. And also another thing is that it is very compatible with the CSR format for those matrices. Okay, so the next one is to design the hardware to actually use that data flow. So here we have the high-level architecture will have 3 components or 2 components. One is the multiply PE, and the other one is the addition PE. So this one will do the window multiplication, the A matrix window times the corresponding B matrix rows, and then the partial sums will be accumulated by the addition PE. So here we design the number of we design the number of multipliers to be equal to the window size. Okay, And then basically this multiplier will be corresponding to the 4 elements we mentioned before. Okay, and to match this one times this row, and this element times this row, and this element times this row. These are 4 multiplications mapped to the 4 processing elements in our hardware. Okay, and then we have the like a very flexible reduction tree here to be able to flexibly accumulate those rows together to be the output matrix. And then we have some sort array, like for each pair of these multipliers, we can do some local load balancing between these label lanes. For example, if one lane finish first, we can put the multiplication task of the other lane to this one, and to do some local load balance in this case. And finally, we have some queues to ensure the order, because like when you do the application, you need to pay attention to the order of the thing. This is a very tricky details that we will not talk about here, but if you are interested, you can look at the paper. Okay, then the policy part. Okay, so we basically try to, we have some key insight here, like the similar, like for a specific matrix, the sparsity pattern are similar within the local rows. Okay, maybe like you see, like the local field rows, they have similar sparsity patterns, so that we call it a band. Okay, so here we see a few rows will share the similar sparsity, and then maybe it gradually become more sparse or gradually become more dense, and so that we have a local band of few rows, and we use the same policy for this local band. And we identify this band by using the non-zero row length. Okay, how many non-zeros in this row to identify this band. Okay, and then at runtime we will just say for each band, for example, here this is a local band and this is another local band because they have similar non-zero size, and this is another local band and similar here. Okay, and at runtime we will first we offline partition the matrix into these banks by looking at their non-zero row length, and then we at runtime. For each band, we will just do some profiling of the first few rows to determine which one is the best policy, which is the best window size. And then we use this best window size for the rest of the rows in the band. So the result, when we compare with some of the state-of-the-art baselines, we can see that each of these baselines are using a specific one of the data flow choices, but we are more flexible and can be adaptive among these 3. And you can see that we are always the best among the 3 baselines. That means our architecture is able to adapt to the best data flow choices among the baselines. And overall, if we take an average, we have achieved 1.4 times speed up in this case. Okay, the second part is the loop tiling part. Okay, so remember that the loop tiling is trying to split a large matrix into some small tiles. Okay, like we have a large matrix, and then we have each of these small tiles, and then each small tile will be able to fit in the on-chip buffer to compute. But again, the challenge is that the sparsity varies a lot. Some tiles are quite dense, while the other tiles are more sparse. For example, in this case, maybe this region is very sparse. There's only a few non-zero elements, but this one is very dense. Okay, it has many non-zeros. For these sparse tiles, the number of non-zeros will be smaller than the on-chip buffer size. Okay, so you are underutilizing the buffer size. But this one, you have too many non-zero elements, so it maybe will overflow. So the on-chip buffer is not enough to keep all the non-zeros in this tile. And you can see that there's also across matrices, there's dense or sparse matrices, and even inside one matrix, there's dense and sparse regions. Okay, so our tiling approach needs to be adaptive to this local density of the tile. Okay, so we propose another work which is just presented in ISCA 2025, like last month, which is to make the tiling decisions also adaptive to the sparse patterns. Okay, so we first demonstrate like tiling schemes, like what we need to decide for these tiling decisions. Okay, like the tiling size, tiling shape, etc. We demonstrate the comprehensive, the full design space of sparse tiling. And then we use a static and a dynamic hybrid approach. And at static time, at offline time, we use a lightweight sampling approach to identify some near optimal tiling size, okay, for the initial part. And then at runtime, our hardware is able to dynamically fine-tune to adjust the initial tile size to be adaptive to the local regions. Okay, so if you look at the problem, so here assume that we have a A matrix times B matrix, and this ik dimension times the kj dimension. So first of all, we have and assume that we have the tiling. Okay, A is tiling to this 2 times 3 regions, and B is like 3 regions here. And first of all, we have what we have just mentioned. Oops. The animation have some issues. Okay, so if you look at the size of the tile, okay, which is the number of non-zeros in the tile, we just mentioned that some of them have many non-zeros, so maybe overflow the buffer size, while the others have like underutilized buffer size. But also the tile shape is also have some effect on the problem. So if you look at the I dimension, okay, so here we tile it into 2 tiles along the I dimension. But you see that both of these 2 dimensions, like for this one, it needs to times all the 3 tiles of B. And for this one, it needs to also times with the 3 dimension of B. So how many tiles along the I dimension will determine how many accesses, how many repetitive accesses we need to access the B matrix. Okay, so you make this tile too small, that also means that you will access the B matrix too many times. Okay, so there's another trade-off here. And finally, the intertile order. Okay, so if we go this way first, then you can see that we will process these 2 tiles together, and that will reuse the same B matrices first. Okay, so this one will times with all these 3. This one will times with this one, and that one will also multiply with this one. Okay, and then this one for this one. Okay, so if you go along I first, you will be able to reuse B. On the other hand, you can imagine if you go this way, you will actually reuse C, but not be able to reuse B. Okay, again, there's a trade-off of data reuse here. Okay, there's also more choices that we do not have time to mention here, but you can see the paper. So that brings to the question that we need to estimate the performance for each tiling decisions. Okay, the tile size, tile shape, for a specific choice, which one give us the best performance. In order to estimate the performance, we need to estimate this like non-zeros of A matrix, non-zeros of B matrix, and also C matrix, and also the total amount of MAC operations, multiply add operations. Those are the data size that determine the data access performance, and this one is the commutation amount, determine the commutation amount. So for A and B, the non-zero size is easy to know because these are the input data. But for C, it's unknown because this is the output. Like you can now know how many data you have before you get the C matrix. And also similar for MAC, because this number of MAC operations determine on their correlation between A and B. Okay, so we need to have a way to estimate these numbers. And furthermore, if we tile along the K dimension, we actually have more C partial sum of the C matrix that need to estimate. Okay, so here we use a sample-based approach that we just sample a few A rows and few B rows and to estimate their total amount. And there's like the equation here. We will not go to the details. And finally, we have dynamic tuning. For example, here we use some counters to count each local, like smaller region, each quantum of the sizes. Like for the whole tile, we have this hit rate. But if you just reduce the size along the K dimension, if you tile in this way, instead of the larger tile, if you reduce the tile size, you'll have a larger estimation of the hit rate. And similar, if you tile this way, you have another estimation. So you use some on-chip like dynamic counters to count the number of accesses and choose the best one. Okay. Due to time limit, I will not go to details. Sorry for that. And quickly for the result, we are able to outperform some of the previous baselines because of this adaptability to the local data regions. And there's like 3 times or to 6 times speed up in this case. Okay, to summarize, basically we are trying to investigate the loop reordering and tiling approaches for sparse accelerators. Okay, so this work is for loop reordering and this one is for loop tiling. And we have like a hardware and software co-design approach. Here we have a reconfigurable hardware and then a policy to decide which one to use. And here we have a simple static scheduling before, and then on the runtime, we dynamically fine-tune the decision. Okay, so that's all for my talk. Okay, I'm happy to take any questions.
Thank you very much. Since I was an undergrad student, matrix multiplication is a problem that we still have to work at. We have time for a quick question.
Hi, my name is Lucas. So basically, you're arguing that sparta and height are gonna accelerate with matrix multiplication, correctly? Yes.
Yes.
What are the downsides of sparta and height?
What do you mean?
If given the normal way of doing matrix multiplications with sparsity, with low density, what are the downsides of this operation? Sparta and height.
So, okay, so those are mostly for large size matrices. Like it has to be loop tiling and reordering. They are for like large sizes. If your matrix is small enough to directly fit in the on-chip cache or on-chip buffer, you do not need to use this tiling and reordering techniques because you just bring all data on chip and compute and then get it out, right? So that's one. And also the design may be a little bit more complex, okay? So for example, for those cases we mentioned, it will only add the hardware complexity, but without any benefit. So that's probably the some of the limitations of this work. And there's many other things. For example, the detail of the buffer design actually have some other issues that we are currently looking into, like the replacement policy, like how you try to keep data on chip, etc. Those are some orthogonal works that we are also trying to consider.
Okay, thank you.
Okay, thank you.
Good presentation.
Thank you.
Thank you again for your excellent presentation.
Okay, thank you.
I'd like to now invite our second speaker, Nelson, who is going to talk about RVA, a RISC-V instruction set architecture flow analyzer. He's from Alberta, and the presentation will be already open. And Sandro is going over there.
Did you download it in PowerPoint or not?
Sandro?
You download the PowerPoint? While he is setting up the presentation, let me give you the intro. I will assume that some of you may not know flow optimization compilers. So I'm going to give you a lecture about that today. But let me motivate why we are doing this. I teach a second-year undergrad computer architecture course at University of Alberta. Last January, we started with 315 students. The students write very complex RISC assembly code during this course. They have 5 assignments. The last assignment may be, for example, a binary translation of a subset of RISC-V instructions into ARM instructions. They have to write the translator in RISC-V assembly. And they have to build, for example, a control flow graph for a binary of a RISC-V program and compute the dominance relations and that kind of thing. Why do I bring these concepts to my computer architecture course? Because I am a compiler guy. And I do something that I call stealth teaching. While I just tell them, you have this assignment to do. I don't tell them that they are learning a whole bunch of other concepts while doing the assignment. So that's the motivation. So for the professors in the room, have you ever had a situation where you think, oh, this is a cool idea. I'm going to get a summer student to do this in 3 months. And then you find yourself work on the same thing 2 years later? Yeah. So this is one of those stories. So what we are trying to do here is, first of all, the motivation is that I have this large group of students who are programming for the first time in assembly, and they are programming in RISC-V assembly. They are using what is called the RISC-V Assembler and Runtime Simulator, or RARS. It's a totally functional simulator. What it allows you to do is to follow the execution of your program and see the modification in all the registers, etc. So that's the environment where they are working. However, if you are programming in assembly for the first time, it's likely that you're going to make mistakes. And if you don't have a tool like your usual programming tools to find these mistakes, you may find yourself spending lots of time trying to find these mistakes. So our idea is that we will create a tool to help the students find mistakes into their assembly code. So before I can tell you about the tool, I need to give a little lecture on RISC-V assembly, especially about the calling conventions. That's one of the things that we teach our students. So like many other architectures, RISC-V has a calling convention. So here what I'm illustrating is that there is a function foo, and this function is calling a function bar. This is how you call a function in RISC-V assembly. And we have some conventions. So here's my function bar. And the conventions is that at the point immediately before the call and the point immediately after the call, the values of our S registers should be the same, as well as values of SP, FP, GP, etc. So there is a set of registers that we have a contract with our callee that those values should not change. And then the values that were in the A register and the T registers immediately after this call are unknown, because our contract is that the callee can change those values at will, and anything that I had in those values before, I have to assume that it's lost. And the convention is that the registers A0 to A7 are arguments to a function, and the registers A0 to A2 are return values to the function. So these are just conventions. We could have a different convention. So our analysis actually accepts a general convention. You can define what your convention is. If we are doing RISC-V, we're going to use this convention that is the convention. So what we have is that there is a register called the return address register. That is, when you do a function call, the value of the address immediately after the call will be stored into the return address register. So what happens here is that foo got called. So when foo starts, the return address for foo is in array. And then when I call bar, now the return address for bar will be written in array. So therefore, foo must save the value of array into a stack so that it can restore it before returning to its caller. So I told you that it will be a short lecture on RISC-V assembly. So what we have a stack, and where we're going to save registers is we're going to move the value of the stack pointer to create room into the stack for the frame of the function that we are calling. So that's the way it works. So the students also have to manipulate this stack. Okay. So what are common errors that I have seen in my midterm and final exams when I ask students to write relatively complex assembly code? Typical things here is a function. It's a bubble sort function. I have written it not in assembly because for people that are not initiated it might be harder to read, but people that know assembly will see that each one of those lines can immediately be translated into an assembly instruction. And what we have here is a function called swap that's called by this function sort. So it's a bubble sort that calls a swap function. This is, if you're familiar with the Patterson-Hennessy book, this is an example from the book. And I made some mistakes. For example, I wrote this value into S1, and S1 is not used anywhere else in the code, so that statement is dead. I also, now I had made a mistake, so now I tested the value of T1, but the value T1 has never been initialized, so I have an access to the value of in a register that has never been initialized. And now what I have in here is something similar, but what happens is that I just call the function swap. And remember, my assumption is that after returning from a function, none of the T values have anything that I should care about. So here I have an unknown value in T1 after a function call. So those are some examples of errors that students could commonly make while writing assembly code. So what do we want? We want a lint tool that the students can provide their written assembly code, and this lint tool will point these errors to them. We are not integrating our tool into RARs. For the typical problems of user interface design and updates and such, we don't want to mess with that. We're going to give them a separate command line lint tool that they can run their code and help them find the code. So one of the things that we're going to do is something that's known in compilers as a liveness analysis. Liveness analysis is a well-established technique. I'm going to teach this to you right now, but we're going to do it based on registers instead of based on the values of variable. So what we're going to do first, we're going to take this code, and we're going to identify the basic block leaders in this code. Basic block leaders are the instructions that start a basic block. And they are very easy to identify. The first instruction of a program is always a leader. Any instruction that is the target of a branch will be a leader. And then any instruction that, what's the third rule? Has to be the first instruction, has to be the target of a leader, or after a branch, you always have a leader, because the branch has to be the last instruction of a basic block. So identify the leaders. Now that I have the leaders, I can identify the basic blocks. And now I can re-represent my program as a collection of basic blocks. And now I can represent the flow of control from the original program, and that will give me a control flow graph for this program. So now that I have that, I can start doing my liveness analysis. In this example, I'm going to assume that when this function returns, it does not return any value. So the registers that contain a value that I care about, those are called live registers, is a null set in this example, which is through the sort function actually sort the values in a vector, but does not return any value. So now that I have that, I can propagate this information through my return statement, and I still have an empty set at the point before the statement. Now I can propagate this information to the predecessor block. I always do liveness analysis as a reverse topological sort of my control flow. So I still have an empty set, so there are no registers live there. And then when I pass this statement at those 2 points here, I'm going to have that the registers S0 and S3 are live, because they just got used in this statement, so they must be live at that point. And I can keep doing that. You guys understood what I'm doing now. Every time that I use a register, it is added to the live set. So S0 is used here. So I have a value for S0 there, and so on. And here I use T1, so now I have added T1 to my live set. And I keep propagating. I'm at this point. And now I have a question. This is a function call to swap. And what I have here is that the live registers here are S0, S3, and T1. And the question is, what are the live registers at the point immediately before swap? And why do I pause here? Because this is where doing it for registers using calling conventions now make my liveness analysis different than the liveness analysis that I have taught in my graduate classes in compilers. Because now I have to reason about the calling convention to decide what's live before that function call. So what was a trivial problem until now, suddenly I have a decision to make. So let's go back and let's understand that because I'm trying to enforce the calling conventions, my analysis is going to have to be interprocedural. So now what I'm going to do is I'm going to look at the swap function, because what I have in between those 2 points is the execution of the swap function. And I will do the same thing that I did for my sort function to my swap function. I will find the basic block leaders. This function only has one basic block, so it only has one leader. I'll represent this as with this control flow graph here. And the question now is, what is live at this point? And remember that I may have hundreds of calls to this function in my program. It's not just one call. So I have some decisions to make. So I may have many calls to this function. And the answer is that I'm going to decide that the out of my function bar will be X, so that X is in the out of any call to bar. So I'm going to do a union of the registers that are live at the point of all the calls to bar. But I also say that X cannot be, the X has to be a return register, because those are the only registers that I will consider as being live after a function call. So a register has to be a return value to be live. And you may be thinking, I know that Victor is thinking like, oh, but how about the S registers? I'm going to keep them aside, okay, to make my analysis simpler. So only the argument registers are in the inset of a function. And so because what I had before didn't have any the argument registers, what I have when I do the propagation here is that only A0 and A1 will be live at the input of that function. And what I want to do is to analyze each function just once. But for this, I'm going to have to do an earlier pass to find all the argument registers that are live at the output of all the calls. So back to my problem, I have to decide what's live here. And now with these assumptions, I can decide that what's live here is A0 and A1. What has happened in between those two is that, remember, I kept the S0 and S3 aside, and I propagate in this call. So all the S registers that are live after a call will be live before the call, because I'm assuming that the function is following the calling conventions. So I also told you that the students have to do stack manipulation to create a frame for the callee. And if I want to analyze and help the students with the stack manipulation, there are two additional things that I have to do. I'm going to have to do a value analysis, and I'm going to have to model access to memory. What I want to do, I did not tell you when I gave the code before, but there will be code like this that will be at the beginning and the end of each function to save the registers into the stack and restore the registers from the stack. What happens is that the students make mistakes in this code as well. Here, I made several mistakes just to illustrate the type of mistakes that I have seen when grading exams. I may and by the way, if you do a mistake like this, and you are debugging using vars, it's going to take you a long time to figure out where your mistake, because what happens is that the function is returning and has messed up the stack and is messing up many other functions, but you don't know that the error is in this function. So what I want to do to help the students here is, so first the errors. This is a misaligned value of SP because it's not a multiple of 4. This, I'm storing S0 and S1 into the same memory position. And I am modifying S3 without saving it now because I forgot to do the saving. And here, I restore the registers in the wrong order. So I save the value, for example, of S0 in SP plus 4, but I'm restoring it from SP plus 16. So this, I introduce many mistakes in here to illustrate the types of mistakes that students will make. And what I want to do now is to figure out how I can help the students to do that. So the way I'm going to help the students is to do something that's called abstract interpretation. I'm going to interpret each one of the assembly instructions and try to figure out how the assembly instructions is changing the values in the memory and in the registers, and I'm going to use value propagation to do that. So the idea is that I could have, for example, this code here. This code has no errors, but if you see, I'm using different registers, and I'm making all kinds of operations with values here to determine the address of this memory operation. I want my analysis to be able to go through this and figure out that the address that I'm restoring the value of S3 here is the same address where I have written S3 there. Just to illustrate to you that this value propagation and abstract interpretation has to analyze arbitrary code. Okay, so this works. I have to handle eCalls. If you're familiar with eCalls, I have a modeling for eCalls. The analysis does that as well. So we have this lint tool. The lint tool, this is a demonstration of the lint tool in action, and just illustrates to you the kinds of errors that the student will gonna get when the student lint the program. Okay, so we are happy doing that. And then we had a presentation of this work at CASCON in November, and there are colleagues from the Huawei Canada software lab there, from the compiler group, and they said, wait a minute, this is extremely useful for us. We want this. And I go like, why do you want this? And the answer is, we have new processor designs for which there are no compilers. And we are writing initially assembly code to demonstrate that this new design is going to work. And we make mistakes just like your students. And our developers may spend days figuring out this mistake. And the other use is that we have compilers where the code generator is being changed. And we make a mistake in the code generator that produces wrong assembly. And we spend days trying to figure out what went wrong. So with that, we start porting to demonstrate that this analysis is flexible to ARM ISA, because they do use ARM as a design point. And we are in the process of doing that right now. Summarizing, what we did is we start with programming assembly by students. We discussed the calling conventions for RISC-V. I gave you a little lecture on that. We talk about lives in analysis. And then we show that we also need value analysis and abstract interpretation. And we show that we have a lint tool that's working, and that we need to now adapt it to other processors in order to make it useful to design teams. Thank you very much.
Thank you very much, Nelson. Amazing talk. He started helping students, and now he's helping big techs. This is nice. A quick question.
Hey, Nelson, nice presentation. I want to know about ARM. When porting this tool for ARM, not only you have to take into consideration the calling conventions, but what else changes? What are other things that are particular to that architecture?
The representation of values in ARM is different than the representation of values in RISC-V. They have this variable range of values. So our value analysis has to adapt to that. That's one of the things that we have to do. But there are a few other details that we need to work.
Okay, thank you. I'll talk to him.
Yeah, we're going to have to talk to me, Victor. The usual suspects.
Yeah. Thank you very much. So, trying to keep the schedule, Ricardo from Federal University of Mato Grosso do Sul is going to talk to us now about approximate instruction set architectures in RISC-V. Please, Ricardo.
Hello, everyone. Good morning. So I'm Ricardo, as Alfredo said. I'm from the Federal University of Mato Grosso do Sul, and today I'm going to present you. It's a summary of a set of works we have done in our research group at UFMS. So this is the agenda. I will introduce something about our work and specifically about approximate insertions, and then I will try to show you some applications of our approximate insertions in software techniques for approximation, and then some final remarks. Well, this presentation was based on the following references that our research group has working on approximation techniques from almost 80 years, and so we have the most recent publications that describe many things I will present to you today. Everybody knows about Moore law and Dennard scale, and so we are facing the end of these two guidelines to design new technologies, and then so we are facing on challenges to find new alternatives, and approximate computing can be such an alternative. Once that's a promising approach, there are a variety of techniques. It's, for decades, people from academia and industry have proposed different approaches from circuit level to the application level, right? Well, but approximate computing has a specific, set of applications or let us say things to do because they are constrained for that the application should tolerate some lack of accuracy, and so not all the applications can tolerate that, but for those who can support some laws of accuracy, they can give you some points in order to improve performance, or even, and that are the most the most goal of approximate computing, that is save energy consumption. Well, this is a very simple example where we use an application. It's called Caminhos from X's benchmark. That is, we just replace some of the sub operations for sub-X instructions. Sub-X are, I will show you, are sub instructions that are approximated, and then you have a quite similar result. Well, so in terms of software level, there are many techniques in approximate computing, and so one of them is called a loop perforation. That is quite simple. The idea is to identify the control variable in loops, and then to substitute for another step. Okay, so in order to do that, of course, the compiler or the software assisting this optimization should observe, should check if the step that I am changing is could provide a good result or a tolerate result for the application. So the idea here is that, so I can, approximate my software, but I have underlying hardware that is still accurate, that's still exact. So our idea is to try to investigate if you can, even if you use software approximations, what's going on if we use also a hardware or instructions approximated. So, and then we design, that's our work, it's design approximation instructions, on the top of RISC-V ISA. And so the applicability is on some software approximate techniques like loop perforation, approximation functions, and then in design space exploration, try to look at a wider region of the software in order to substitute accurate instructions for approximate instructions. Well, and then approximate instructions, in our case, is built on the top of arithmetic circuits. So first of all, we design some arithmetic circuits, approximate arithmetic circuits, and then we start to design some, a small subset of arithmetic instructions, integer and floating point, using the RISC-V instruction set, right? And as a software support, you use the ACCEPT framework for software approximations. ACCEPT has, a quite large set of software approximations, and what we have done in our group is that add or approximations using approximate instructions in that software software framework, right? So that's the idea, where when you have an application, the user can set or choose this the operations or the code lines that he want to apply approximations, and then he can also choose if he will choose software, only software, that is the number 6, or a mix between instructions and software approximations, right? So the final code is in RISC-V, and we also redesign the Spike simulator. Is a very well-known simulator for RISC-V applications, and we work on that. So when we talk on approximate circuits, the idea is also very simple. Once that we have, a library of options for approximate circuits to substitute accurate or exact circuits, like adders, subtractors, multipliers, and so on. There are also freely and largely available libraries for multiplications and so on. So from those circuits, from those approximated circuits, we start to design new instructions. You can see here a set of instructions with the X in the end. So these instructions are new, and we start to develop those instructions in the Spike simulator, right? So we take advantage of some open bits in the opcodes fields in the RISC-V ISA. Well, in the Spike simulator, we have changed some. Actually, we have added those new instructions, and so the idea is also straight. Once that we have to use the same pattern to add new instructions, but also pay attention on the operations in order to include or to use the approximated ones. But a challenge appears when we design floating point instructions. Once that those instructions, this is an example of a floating point add, can be used also for floating point sub. There is many points in this, in this block diagram that we can use instructions. So in that kind of design, you have to pay attention on the design space exploration. So the question is, what are the basic instructions you put on that block diagram, or are you substituting that block diagram in order to have add floating point, approximate, right? We have many points here, and so just for an example, we can substitute the adds, the simple integer adds that are in this big ALU component, right? So there are also sub instructions that can substitute for sub-X instructions. The same idea happens for all the instructions for all the floating point instructions, right? They are complex, and so there you have to take a careful look at the points where you have to or you could substitute your instructions for approximated ones, right? So here you have different points and many options that you can do. So what we have done here was to design this integer and floating point instructions based on an exhaustive search to provide floating point approximate instructions, but not to have a large error, right? So of course, depending on the user choice, there are different combinations of designs that can use for provide floating point approximate instructions. But once that we have your instructions, your arithmetic instructions, the other point is, so I have to, or I should, use my instructions in that piece of code right over here. And so you can see here we are many different points. For example, we have a sub, you have a multiply, you have divide, you have add, you have different operations over here where you can use your instructions. The idea where or what instructions I should substitute for approximated ones. So there is another point of another subject for design space exploration. And so in our case, we use just one instructions in order to follow some user thresholds of error. Well, this is just to show a little bit the opportunities for using approximate instructions in some very well-known mathematical functions like sine, cosine, tangent, and so on, right? You have, so in almost, in all of them, you can use approximate instructions. And so, what you have done here was an experiment where if you use those instructions that have the number, you have a small error at the end. Though going further, going to the up, so once you have changed the operations, sine, cosine, and so on, when you use that on applications, for example, you have just 5 applications here, you have different points where those functions are called in the applications, right? So the other discussion here, or the other challenge, is where I should use my approximated approach that you can see now that I have, I have approximate circuits using for approximate instructions that are using in mathematical functions. And those mathematical functions are using applications, right? So this table here showed the number of callings that are in each application, and in parentheses, they are the ones that we have replaced for approximated approach. Well, so when you look at the applications, you can see some, improvements, mostly in energy or power, right? You can see here in the Black School application. And from those approaches that you have used, mostly on instruction level loop perforation and then instruction level approximated functions. So a question that have come out in our research group was, if you extend a little bit, the usage of our instructions straight to the code, right? So instead of use only in loops or only in approximated functions, if we look at in a function, and you try to substitute the operations for the approximated ones. That's the idea, right? So you have, a small piece of code. If you change everything, you can, you have this as a result. But the thing is, this will provide, a good result in terms of accuracy and power improvement. So what we have done is, you have designed a heuristic approach based on branch and bound, where you look at, all the combinations, right? But you have, a very deep pruned strategy in order to cut some branches or some subtrees to expand, the total time of the heuristic, right? So this approach is very interesting because in these 2 graphs here, you can see in the triangle the result for the non-approximated code, the accurated code. And for those who can see blue here, the blue is the options where you insert approximations, but these approximations do not, are inside the toleration threshold that the user establish. And the red points are the lack of accuracy beyond the error threshold, right? So you can see that even using some approximations, can have your results can be much worse. And then this table is the last one. I will show you some interesting results in terms of energy savings when you use an approach like that. Like, try to see the right points to substitute instructions for approximated ones, right? You can we have that on your papers. So as a conclusion, we have designed approximate techniques supported by a set of new approximate institutions in RISC-V. The results on energy savings are really significant and meet user constraints on error thresholds. And so we are still facing some limitations. We have some ongoing work to do. And so we have software. Unfortunately, I didn't put here the link, but I can provide for you offline. You have this, freely available for anyone, right? So thank you very much.
Thank you very much, Ricardo. Approximate computing is a hot topic. We have kind of the last Gordon Bell was done to approximate computing. So one quick question.
Thanks for the talk. Quick question. How do you measure the energy? How do you evaluate the energy of your benchmarks?
It's a really good question. We have a previous work, not from us, from the literature, that we have designed those instructions with the same approximated hardware, the same approximated circuits. And these authors have measured the difference between non-approximated and approximated. So we have used the same proportion of difference between, power consumption, energy consumption used.
Okay, but you do not evaluate the benchmarks in a real RISC-V core, for example?
No, unfortunately not.
It's only evaluation made on instructions profile.
Based on simulation.
Okay, thank you.
So thank you again, Ricardo. So we have the last presentation of this section from Roman Shaposnik. He's already there. Thank you, Roman, to be on time. Demystifying low-level AI infrastructure. Roman, the floor is yours. Please, go ahead. We are not hearing you. Maybe it's here.
Hello.
Okay, we are hearing you. Please, go ahead.
Okay, so if you can hear me, can you see my slides?
No, just a black screen.
Okay, let me try this. What about now?
Perfect. Go ahead.
Okay. So hi, everyone. My name is Roman, and I happen to be a co-founder of the AI computing company based on RISC-V. I also happen to be one of the members of the community called AI Foundry, to which I hope to invite you all because it's an open source community trying to build the AI acceleration infrastructure. Now, you may be asking yourself a question. Why is the guy who is clearly doing AI talking to us at the RISC-V conference? Well, I happen to believe that every era in computing basically gets created by a use case and an architecture to support that use case. So for example, a long time ago, we had an age of mini and personal computing, and Intel obviously ended up as a dominant architecture. As you all know, at some point, maybe around 2003, we ended up having an age of mobile computing, and as we all know, ARM became the dominant platform. I will try to convince you that we are basically witnessing the age of AI computing, and I will try to convince you that AI computing is actually different from all the previous types of computing. And I also will try to encourage you to think that RISC-V is uniquely suited to be a winner in the AI computing space. Now, what is AI computing? A lot of people are familiar with it through just using of OpenAI. That was a global phenomenon that effectively changed our industry. And if you think about it, the OpenAI APIs are deceptively simple. You basically send this kind of a formatted request and effectively just specifying a few parameters. You're basically asking AI, generative AI model some questions. Maybe you will try to do completion, and it will produce an answer that will be, again, deceptively similar to talking to a human being in a lot of cases. Now, I don't believe for a second that we are close to anything like AGI, but it is absolutely undeniable that this type of services are very, very useful. I use OpenAI, I use ChatGPT all the time, and just helping me with all sorts of tasks, ranging from running a company all the way to coding. But if you ask yourself, what do we use to build a machine, to build a farm or a cluster to serve up those types of APIs? Well, we used to know how to build those things, right? And in the open source community, a standard emerged. That standard was and still is called LAMP for Linux, Apache, MySQL, and PHP. And the combination of those technologies running typically on Intel, maybe with a few exceptions nowadays, ARM servers, would provide you with this type of API being given to your clients. So can we use the same stack to build what a OpenAPI has built? The answer is absolutely a resounding no. So OpenAI, in fact, built a very specialized cluster. It's a compute farm, if you will, that effectively has layers, that start at the hardware layer, being sort of similar to what you would expect, but then, diverging pretty quickly. Now, today, I will be talking mostly about these layers. I will not be talking about model layers and machine learning frameworks. I will touch upon them a little bit, and I will definitely not be talking about application and serving layers. But everything, from the bottom up, I will try to touch and explain to you what are the projects that are interesting and how you can participate in open source development of these layers. But this is to just impress upon you that we're definitely talking about way more letters than just 4 in LAMP. Now, before we go any further, let me basically take a moment and point out that AI actually consists of 2 steps or 2 phases, if you will. So there is a training phase and there is an inference phase. Now, in training, you effectively try to teach the model what to do, and in inference is asking that model to do what you think you was able to teach it what to do. By this year, by 2025, it is actually absolutely clear that the business requirements for training and inference have completely bifurcated. In fact, if you look at training is now being done by only a handful of companies. But the good news is that the market forces have made it so that these types of companies make their models available by and large, not all and not all the time, but a lot of models are freely available. And that dramatically reduced the need of the enterprises to actually train the models from scratch. Now, training actually still resembles, old school HPC market. So anybody familiar with high performance computing would find the architecture is pretty similar. But if you look at the inference as a separate special area, then it is pretty clear that it will dominate training, just simply because training a model takes a lot of time. But once you're done training it, you can actually use it over and over and over again without changing too much. Again, you still need to do a little bit fine-tuning. And there are various techniques of what you can do with the model that has been trained, but by and large you don't have to throw huge training exercise at it. Now, if you forget everything from the slide, just remember this. Training is different from inference because in training you absolutely have to do the smoothness of IEEE floating point implementation, because otherwise it's pretty difficult to make the compute phase converge. In inference, in fact, you don't really need floating point, and a lot of techniques would just make you use integer. So that alone, for somebody who is designing a CPU architecture, should be enough of a reason to give you pause and make you think, hey, maybe the kind of architecture that we're building for training should be different from what we're building for inference. Now, again, if you think about inference stacks, what could be this, LAMP stack, that we can give our customers, especially hopefully most of the components of which will be open source, and make them do all those wonderful things that DeepSeek and OpenAI are capable of doing when we're calling their APIs. Now, this is one of the ways of looking at this stack. And again, slides will be available so you can study it. But this came only a month or two ago from a venture capitalist fund in Silicon Valley called Wing Ventures. And these people are trying to predict, how this landscape will look like. Obviously, for the reasons of trying to invest in certain technologies and just trying to guess which technologies would win. Now, if you look at this stack, it's not totally wrong, right? You basically have a lot of, at the bottom, you kind of have the infrastructure. The problem with that infrastructure is that most of it's cloud-based, and even the one that it isn't, it still bottoms out at NVIDIA. Now, NVIDIA is sort of this huge elephant in the room, whether it comes to training or inference, that basically dominates the hardware landscape. And everybody, especially, in the closed source and proprietary world, is sort of, kind of resigned that NVIDIA will forever remain what it is. Although there are a few companies, and you can see them weirdly enough on the right, Cerebras, Grok, and Samba Nova. I mean, they are kind of cloud providers, but they also build their own hardware, so they don't use NVIDIA. And that hardware is super optimized, it's very, very different, but it's also very, very proprietary. So the first question I have to ask about this picture is why there are no challengers to NVIDIA on this picture, right? Why is there no AMD at least, or some of the new companies that have emerged to basically tackle the same use cases? And I think the answer is, as always, the software, or to be more precise, the CUDA moat. Now, there's this notion in business of creating a moat, and hopefully filling it with crocodiles with lasers around your business that would prevent your competitors from attacking your business. It's like building a castle and, again, creating this sort of fortification around it. Today, it's undeniable that all of the software that runs on NVIDIA is basically bottoms out at CUDA. CUDA is the framework that NVIDIA has created. But the interesting thing is that CUDA was used in AI in a very accidental way, which kind of gets you to think about, how this whole industry has evolved. And if you ask me, I would say that we had basically these ages, blocks of time in AI evolution. And I try to summarize them here. So on the left, you basically see the kind of like roughly the years when it was introduced. And then, you have the machine learning network architecture that was dominant. Then you have the software API, and then you have the hardware on which that network was trained. So arguably, this whole industry got kickstarted, a long time ago, during the 60s, and some of the basic mathematics that we're still using dates back to those times. But the deep learning, machine learning, as we know it today, arguably started in 2012 when AlexNet got released and won basically all the awards in the space of computer vision, basically beating all the more specialized models. One of the reasons it was so successful is not only because the architecture of it was innovative, which undeniably it was, but also because this guy by the name Ilya Sutskever figured out how to use something that wasn't supposed to be used for AI, NVIDIA GPUs, with the help of, I wouldn't even call it CUDA and PTX, maybe. Actually, it's very instructive to take a look at the source code that just got released by the Computer History Museum. So, once this presentation is done, I highly encourage you to Google AlexNet Computer History Museum, and you will get to the GitHub page of that implementation. You will get to see how many hoops Ilya had to jump through to basically make that model run on GPUs. But again, arguably, it kickstarted the whole industry. And then, we had, from then on, co-evolution of transformers. Transformers were done by Google, and that's, what powers up ChatGPT today. But again, that co-evolution was done between the framework that is called TensorFlow and Google TPU. Then again, arguably, everybody sort of standardized on kind of like GPT type of architectures. PyTorch was the dominant framework. And the architecture was still NVIDIA and maybe some AMDs. So today in 2025, we're running transformers, obviously. But what is the framework? And what is the architecture that we will be running it on? So again, allow me to sort of paint broad categories. And this is here mostly to basically make you think about those things, right? So you've got on the accelerator side, you've got Tenstorrent, you've got my company. On the framework side, you've got VLLM, TinyGrad, ZML, GGML, Llama CPP. If you're unfamiliar with any of those projects, I highly encourage you to Google them and maybe join them, because pretty much all of them are open source. And then you basically have providers like Hugging Face. Again, my company is doing some of the layer management APIs. All of these things are typically unfamiliar to people because they all equate AI with PyTorch, maybe CUDA, maybe some of the other frameworks. But there is this whole broad category of new things on the market today, which I think will be the winning category. So again, I highly encourage you to take a look. Now, if you ask me what this winning architecture is going to look like, I would basically say that it will be a RISC-V based, transputer-like many core architecture. So the number of cores should be in thousands. I actually envision, again, we have an architecture in my company that scales up to 4,000 cores, but I probably will be higher. Then you will have specialized frameworks, Llama CPP, things like that. And then you would have sort of very specific compute graph, frameworks to basically map higher level frameworks onto this many core architecture. And why this many core architecture will be different from everything that we've seen before? Well, there's a few personal observations that I have about what makes this thing go fast. Now, again, we already agreed that inference is going to hugely dominate AI market, so I don't have to talk about that. So all the other observations are based on the fact that we're building something for inference. So first of all, for inference, you don't have to build a Turing-complete compute graph evaluation frameworks, right? In fact, Turing completeness is considered harmful because in AI, it so happens that the shape and overall data flow of your computing is known a priori, and only the data that flows through the compute graph changes. So quantization and integers are not just for storage. We basically will be using them for computation. And in fact, I think that int4 and int8 will be the predominant compute data type. I really don't want to see floating point on my inference-focused chips. Like, I think it's a waste of time and silicon real estate. ML frameworks are supposed to be a RISC-reduced instruction set, not CISC. And PyTorch, unfortunately, doesn't fall into that category. So again, we would have to have something new. My biggest takeaway from spending a lot of time in this space is that unless your machine learning framework co-evolves with your silicon, sort of the same way that NVIDIA co-evolved with CUDA and PyTorch, and TPU from Google co-evolved with TensorFlow, unless your ML framework does that, you might as well not do an ML framework. ML frameworks that are not rooted in silicon are absolutely useless. My other observation, again, just being like an old fart in this industry, is that an architecture that was sort of long forgotten, transputers, is finally becoming very fashionable. And I think the transputers of 2025 and beyond will be built as many core RISC-V chips. But the difference compared to the accelerator cards of today will be that those accelerator cards will be full computers just hanging off of your PCIe slot. So again, this is a little bit difficult to get your head around, but think about it this way. You are really using the host computer just for communication and sort of storage management. The actual computation not only happens on accelerator cards, but those accelerator cards are effectively full-fledged computers giving Ethernet type of connectivity back to the host. And effectively, what you're putting in your cluster is the accelerator cards. Again, it takes a little bit to kind of get your head around this new architecture, but I believe that, again, just like transputers in the 80s, that will be something like that. Finally, I would actually encourage you not to follow the crowd, and especially not to follow the crowd of all things to all people. And again, NVIDIA, unfortunately, being a market leader, is sort of trying to be that, and they should, and they're actually really smart engineers, so they're doing a lot of things to be really all things to all people. Again, things like HBM, coherent caches, all of those things are really needed if you're trying to hide what's happening on the side of the accelerator card and only give your customer a very narrow API. But if you don't, then all of a sudden DRAM and scratch spaces, for caches instead of like coherent caches, and basically an Apple M series like architecture where you have, the same sort of memory pool onto which you have a few bigger cores, to run something like Linux, and, thousands upon thousands of smaller cores to basically do number crunching. Those types of architectures are definitely in. So that is my vision for the future of AI inference. There's an organization, like I said, called AI Foundry that is trying to make sure that this future happens in the open source domain. So please join us. We've got a Discord. We're very friendly, and let's build it all together. Just scan a QR code. Thank you so much.
Thank you very much, Roman. We have time for a quick question, comment.
I have two questions, but first I want to say thank you for telling me about this event. I was in Mainline Linux for RISC-V group when you told that you'd
Hi,
come to
Carlos.
Brazil. Hi. And I have already tested some AI stuff with Banana Pi that being honest, this runs Tiny Llama well and no more than this, but she have some custom matrix extensions that are called EMA. I don't know if I pronounce it right, but okay. And you was talking about AI accelerator with a bunch of cores, and this board has two clusters of 4 cores, but one has these matrix extensions, and when you say many cores, how many cores?
Like I'm saying, I'm thinking thousands. So the chip that I have today in my hand, in my company, has 1,000. Since we have the chiplet architecture, we can basically tape out up to 4,000 at this point. But I really would expect it to be in like 10,000, category per chip. Because again, and I have a reason to expect that. I really don't want my compute cores to be all that sophisticated. I really don't want them to have coherent caches. I really don't want them to have floating point. So all of those things that chip designers take their pride in developing, a lot of them I simply don't need. What I get in return is a high, actually tremendous amount of parallelism. And if I couple it, and now comes the tricky part, with a good network on chip, and I have, again, up to 10,000 of these cores, I believe that we will have a much more performant architecture as opposed to building individual cores that are capable of more and more instructions and extensions and, things like that. Now, at the same time, I believe that the architecture of these accelerator cards has to be flexible enough. So again, these cores still have to be, bona fide RISC-V cores, so they have to conform to the specification. But again, a lot of the extensions I simply don't need, which allows me to free real estate on the silicon to basically put a really high number of them on a single chip.
So instead of 5090 with 192 SMs like NVIDIA does, you want to do much more cores, but more
Correct.
simple,
Yeah.
more easy
But
to...
way more simple, yes.
Okay, that's
Actually,
good.
I highly encourage you. So there's a kind of an narrative arc for this architecture. So obviously, again, for old people like myself, there are transputers, but those are in Computer History Museum now. But there was the architecture done by Andreas Olofsson called Epiphany, and he actually managed to tape out a developer board called Parallella. So that was, my first sort of, I guess, eye-opening experience of using, a very massively parallel core architecture for, at the time, DSP, but nowadays AI application, and it just changes how you think about computing.
Okay, Roman, thank you again. I had a question about why RISC-V and not a very specialized thing like Samba Nova, but this is, we can take out offline.
Well, that's another like half hour at least of conversations.
Okay, we have 3 seconds. Could you tell? Okay, do.
Yeah.
I can send an email, don't worry. So thank you again. Thank you very much.
Thank you.
Thank you. So just to remember, we are going to have in 5 minutes the talk from David Patterson. So if you are really hungry, go ahead, get your lunch, and come back. Okay? Eu te dou acesso ao site. Tá fácil.
Sei lá.